pochino più avanti. Dove sta? Perfetto.
Good afternoon, everybody. So it's really a pleasure for me to present Stefano Pelligresi. The first question is he Stefano or is he Jacopo?
Nobody knows.
Nobody knows really. But we call him Stefano. Then Stefano Pelligresi earned his PhD in 2018 in the University of Modena at the physics department with a thesis with cerium oxide grown in Modena and characterized by different spectroscopies. After that, he spent 1 year as a postdoc here at the ISM CNR, working on plasmonics and also cerium oxide with a program employing ultrafast spectroscopy. Then he spent 2 years at the free electron laser Fermi at Electra with experiments, pan-probe experiment, ultrafast pan-probe experiments in the VUV range. And so he will show us also some results that are at the core of this project. And after that, a long journey, 2 years in Genova at the Italian Institute of Technology, working in nanoplasmonics and strong coupling fields. And then, last but not least, 2 years at the Luxottica Research and Development Group in Milan, with the collaboration with Polytechnic of Milano. He won a PhD project, and in this seminar he will present the project and also some scientific results that are at the core of this project. So he successfully brought together different areas such as material science, Polarons, plasmonics, spectroscopy, and nanophotonics. So he was able to construct a project with all the area of his expertise. And in some way, he was inspired by the Roman atmosphere and decided to bring the project here at ISM, and also hopefully with other groups at Artov. Here there is Giorgio Fettinari that is maybe interested in this project. And we hope that this project will be fruitful for future collaboration for everyone interested. Okay, thanks a lot, Stefano.
Thank you, Stefano, for your kind introduction. It's a real pleasure for me to be here, just to show you the result that I will lead here at the ISM. And I'm a little bit when you asked me to take this seminar, I was a little bit nervous since it passed quite a lot from my last scientific seminar. Moreover, Polaron is kind of hard topic, just to be compressed in a few slides, and as I tend to do it in this kind of slides. So okay, stop working. I said that we will. Funzionava. Fino a 5 minuti fa. Sì, no, non so. Questo qui. Produzione troppo buona. Okay.
Intanto poi parliamo
Okay. Obviously, technical issues. Next. Okay, so I just to make a plot of my presentation here, just brief mention the context, my background, and as also Stefano did it just now. Then I will take you an overview of the Polaron. So I will take you the origin of these kind of systems. Then I will talk very briefly about the materials, where they are involved, and also the application. Then I will show you why this kind of structure became in the last 10 years more important for several aspects of material science. And then I will show you just also briefly the experiment where they are involved, as in the thermite reaction. And then I will end with just the idea behind a typical project. Okay, so as Stefano mentioned before, I have a lot of field in my background, so I cover, almost all the possible interaction of the light with the matter, from the surface spectroscopy to photonics, and to also devices and metasurface applications. So just this kind of project is just the closed loop of my background, which brings together all the aspects of my background. However, the atypic project, you can just is born here when I worked with the ISM, with the group of FSL, in collaboration with my former PhD former lab in Modena. And in that case, we were interested in the possibility to enhance the photoactivity of some transition metal oxide, in particular cerium oxide, coupling them with nanoparticles, plasmonic nanoparticles. And this topic led us a lot of paper, and we were very happy about that. However, we also investigate the excitation of the transition metal oxide by itself, without the coupling with plasmonic structures. And we observed that we have this formation of Polaron induced by the light. They say, and this led us also to have other publication also related to this topic. Okay, so now as I said, I take this branch of my career and I put it together with my experience that I did essentially in IIT and Luxottica, that bring all this stuff together to write a typic, which is the accelerated transport of polar in infrared light. Okay, so let's start with some textbook information. So what we the Polaron is just from the definition of Landau, is just the auto-localization of the carrier within an ideal crystal, which is polarized by the presence of this carrier. This concept was, and this state show like very defined state in the gap of the material. Okay. This concept was investigated more in detail by Pekka, which gave this very beautiful definition, which is the strong coupling of carrier with the lattice polarization. So we can imagine the carrier which are covered by this cloud of virtual Polaron phonon. And the result is the fact that we have carrier with increased effective mass. So the mobility is lower than what we can expect from free carrier reproductive band. The first one which tried to attempt to include this kind of the Polaron in a theory was Froelich, which did it for soft lattice, so highly polarizable. And what we have in the Hamiltonian is just the localized electron and phonons. And the term of interaction between them has this behavior, which is 1 over q, which is a signature of long-range polarization. And also this term, which compares is shown also in the alpha constant, give us how strong is the electron phonon coupling. And this term measures how much the ions follow the carriers. On the other side, this approach doesn't work well when alpha is less than 1. And this happened for example, covalent polar systems. So for that kind of system, Holstein proposed another theory where the kinetic part is just given by this integral of hopping. So we have different mechanism of mobility. So we have hopping mobility. We have non-dispersive phonons, which means that we have this bond stretching. Indeed, the lattice is harder. So the autolocalization usually is within the unit cell of the material. And we have also this coupling constant, which if is lower than the energy of the relaxation of the system, induce the autolocalization in the atomic side. Of course, these two theories bring totally different characteristic for the two kind of polarons. So the first one is the extended model, so the large polaron. What happens is that the interaction is long range, as I mentioned. The polar radius is more than the lattice parameter of the unit cell, of course. So it's extended over many lattice units. We have a shallow electronic state, so we have trap state, which are very close to the conduction band, and of course the major fact is that we have more coherent motion of carrier across the lattice, and of course this coherent motion is reduced when we increase the temperature. So the mobility of the system decreases with the temperature. Considering the Holstein polaron, so the small polaron, we have, short-range electron-phonon interaction. The polaron is just localized within as I mentioned, within the unit cell. We have narrow mind gap electronic states, which can, be half of electron volt, so very narrow and very deep. And in this case, the motion is incoherent, so it's phonon assisted. This means that the mobility is increasing with the temperature. Just to mention some material that are involved with large polaron. Polar ionic oxide with wurtzite or rock salt structures, as strontium titanate, for example, but also a light perovskite has this large polaron formation. On the other side, transition metal oxide are quite known that they have small polaron formation and also manganese. Considering the, application or phenomena that are mitigated by polarons, we can mention for the polar ionic oxide the high mobility, and for example the light perovskite, they are very good optoelectronic properties, as the long carrier lifetime could be induced by large Polaron formation. On the other side, which is the most interesting for my research, is the fact that small Polaron is a problem for catalysis or electrocatalysis in those materials, since it modifies the oxygen diffusion. And of course, also for photocatalysis is a problem, because of course we have the carrier localization, which delay the recombination of the electron in the host, but it limits intrinsically the carrier mobility. Just to mention, for the manganite, small Polaron is probably the cause of the colossal magnetoresistance, as I know. Okay, so why this kind of material became, has this renaissance in the last 10, 15 years? That's quite simple, considering that from the 60s and the 70s, the models were very simple, and also when the FT arrives, the unit cell that we can simulate is very small, and also is not optimized for the localization. It was not optimized for the localization of the electrons. Now, and of course, DFT. So for just trying to simulate the large Polaron could have a very high computational cost. Right now, we have a lot of theoretical tools that allow us to, very easy. That allow us to have the correspondence between experiment and theory, and this work both for large Polaron, but also for small Polaron. On the other side, from the applicative point of view, this new wave of Polarons comes from the necessity of understand why some of the transition metal oxide work as not good as they should work. So here is just to mention all the material that can be involved in, for example, photocatalysis, just to have water splitting reaction. If we just want to, take apart the material which has so gap wide that cannot absorb enough light from the sun, we selected also the toxic material and the high cost material, which just have this kind of material. And if you are interested in, for example, in the oxygen evolution, so we just want to use photoanodes. As you can see here, we have transition metal oxide. Just take for 1 second the hematite, which is a very interesting material. The hematite is very interesting because it has a band gap of around 2.1 eV, which allowed it ideally to collect for one reference for the sun, the higher current than the other transition metal oxide. If you consider that the potential efficiency is about 12–30% for the solar to hydrogen efficiency, which is above the threshold for the potential application of this material, it sounds very, very promising, of course. And you have to consider that this material is very easy to access, and could be easy to be implemented, and of course is scalable. However, in the real world, we have totally different efficiency. Usually in real anodes, we can only reach like 2% of efficiency. And the researcher ascribed that to the surface and mid band trap states. which induce short excited lifetime, small hole diffusion, and of course low photoconducibility. However, in the last this paper from the group of Stephen Leone demonstrate that using HHG pulses in order to do pump probe in the XUV demonstrated that they should not be the trap state are not surface or mild trap state, but they are probably due to formation of small pollen. What happened eventually? If we pump the system with energy above the gap, what happens is that the electron is localized over the iron atom, and this generate then deform the lattice and break the symmetry of the 3D state. And they demonstrated with some simulation and using multivariance regression, they found the signal due to the Polaron formation. But they didn't just stop with that. They move forward and try to extract the Polaron formation time and the probability of formation of Polaron with different pump energy. And also using a simple rate equation model, they found that considering the pump energy, if you are, close to the energy required by the system if they are resonant with the transition, they have this formation time which is almost 100 of femtosecond. But if they give to the system more energy, so they here and here you are in resonance with these two T2G and EG transition. But if you give more energy, you have the formation of more phonon, which can interact with the formation of polar. And the Polaron are scattered with the phonon, and the formation probability is lower, and but the formation is faster. Moreover, if you give more energy to those systems, you can have this hopping radius, which means that you make more hopping in the system, and also you have carrier lifetime longer. Consider when you pump just the transition. But what I want to give you as a final message of this paper is that even the trap state in those systems, like the surface of the transition metal oxide, are passivated. The small Polaron localization is just the upper bound for the efficiency of conversion of the solar energy. Okay, so the same experiment could be done also using transient absorption in the visible. If you are lucky as us working with Syria, indeed the characteristic of this material is that Syria has this valence band, which is mainly composed by O2p state, and the real band gap is about 7-8 electron volt. So the conductive band is the cerium 5d states. However, we have this very nice, very localized state, which can be filled because in principle those states are hybridized with the O2p state. So we can also pump those transitions using a visible UV pump, of course. And if you populated them, of course here you have this the map, the transit absorption map. you can see that we have the depletion of the valence state of the valence band, which is reported by this negative absorption after the excitation of the system. And we have also the positive photoinduced absorption induced by the transition from the 4F state to the 5P. You can see also that we have this very fast shift in the transit absorption that we ascribe to the formation of Polaron state, which are below the 4F state. And here is more, is more clear the shift induced by the photoinduced absorption. And we, from the map, we use multivariance regression just to extract the two spectral component. And the first one is the optically excited state, and the other is the Polaron state. We ascribe it to the Polaron state. And if you just consider that the bleaching of the valence band is mainly should be mainly stay at this energy, so for EV, which allow us also to report a proper way to define optical gap of the material. We can only imagine that we have this shift induced by the photoinduced absorption. We, of course, try to fit those spectra. We observe that the shifting of the photoinduced absorption, so the localization of the deformation of the Polaron, induced this blue shift, which is compatible with the Polaron energy formation for the cerium oxide from calculation. Okay, so for now it's just spectroscopy, classical spectroscopy, ultrafast spectroscopy for ideal systems. Now I want just to introduce those Polaron in real world. And this is the case of thermite reaction. I don't know if you know what is thermite. Thermite is just the mixture of different material, usually aluminum powder with hematite powder. And it was discovered and also patented by Goldschmidt in the last 19th century. And he just want to refine material without melting them. And what we have is that if we give to the system a little bit a push in energy push, so heating the sample or using other material to activate the reaction, we have this exothermic reaction, which has this migration of oxygen from the hematite to the aluminum, and we have this formation of iron material and aluminum oxide. We were at Fermi on Electra, and one of our topic was how can we study ultrafast dynamics of reaction, and in particular of this reaction, because using XUV you can probe the two edges from the aluminum and from the iron, and we can, in principle, using free electron laser, we can probe this the changing during the reaction. But the idea was use intense laser pulse just to add the trigger of the reaction. So we did like this sample, which is just an aluminum film, and over we grow hematite, and we did like a raster scan of this for doing the experiment. Why a raster scan? Because of course each time we just hit the sample, we destroy it, of course. And this, you can imagine how much holes are in this sample. But this led us to follow for different energy the dynamics, the electronic dynamics of the two main characters in the reaction. Considering just the aluminum edge, you can see that we have in the first picosecond, we have like the smearing of the edge induced by the electron thermalization. So we induce with the visible pump, we excite the electrons, and we heat a lot the electrons, and they just cool down and induce this smearing of the edge. The other part of the dynamic is just a matter of the expansion of the film induced by the isochoric heating, and these, of course, form a low density region which induce this reduction of absorption at the time. Considering the iron and 3 edges, we have totally different stuff. Also, because you have to consider that we work with like very intense laser, which was below the gap of the material. But of course, we cannot say that we don't have multiphotonics, and so the excitation of the system with more than one photon at time. What we observe is that this is just the map. So we observe this blue shift, which was compatible with what the team of Stephen Leone reported for hematite. Of course, for the longer time, we also observed the same degradation of the aluminum. So the idea was just to repeat this experiment, comparing the thermite with just a film of iron oxide. And what we observed, the blue one is just the iron oxide, the red one is the thermite. And the reduction of this delta E is just the energy where we cross the zero. So you have to imagine the zero crossing from the starting point, and this delta E is like more intense in the case of hematite compared to the thermite. And if you consider that from simulated spectra, hematite should has edge which is at higher energy. So if we have the reduction of the iron oxide or the hematite to iron oxide FeO, we should have a redshift. Probably what we have here is just the two different channels. So we have the formation of Polaron, and contemporary we have also the reduction of hematite. So in this case, Polaron is just a fingerprint that something is happening. Something is also happening. So we have also this reduction. Okay, so now just the inspiration for the project, and the inspiration came from another paper, which is from a group of the Imperial College. And what is very interesting here is that they make this experiment using two visible pulses, infrared pulses. One for exciting the system, and one for pushing the Polaron to again the conductive band. And they just collect the photocurrent from this cathode. And what they observe is that if you are just interested in transient absorption, you just see this behavior, which is, mainly due to the absorption of free carrier after the excitation. You have this one, this behavior, because it's more sensitive. It's more sensitive as optical excitation. Excite the carrier in the conductive band in this case, and the decreasing of the photoinduced absorption is due to the formation of Polaron in that case. Considering the photocurrent, when we use the push, also the push, so just to excite it more the Polaron to the conductive band, they observe this behavior, oscillating behavior, which is due to the coupling of the electron with the particular phonon that they measure. But the main idea was we can, in principle, modify with photon and phonons the mobility of the material. So the main idea of the project was, can we enhance the confinement of the light within the transition metal oxide to create a reservoir of infrared phonon in order to promote the mobility in the material? Just consider, just a very easy photonic crystal, which is the TBR for one direction. Then, of course, this kind of photonic crystal has band gap, which is revealed by the enhancement or reflectance in some particular area of the spectrum. And this means that the photons in this region is not access. The photons are not do not access to the system because they are all reflected. But if we are just on the near the band gap, so where also the transmission is higher, in these regions you should have light that can propagate in the system and has a very low group velocity. Of course, the quality of these resonances depends, of course, from fabrication constraint. In this case, you have this narrow resonances just because you have more repetition of the multilayer. But if you have like here, just a few repetition, those states are more broad, and that means that in that case you have more losses, and of course the velocity is higher. But okay, oh no, other side. So of course you are limited by the fabrication constraint and intrinsic losses of the material, but the idea is lower are the photons within the material, more is the probability that Polaron can absorb those photons. Of course, this is not limited by 1D photonic crystal, but you can imagine the same for 2D or 3D systems. Of course, the distribution of the mode are different. Of course, we are interested in gamma point because the K in that case we can assess to those mode just from the top of the sample. And of course, those kind of systems can be very easily optimized using machine learning methods in order to have inverse design optimization. This is the case of 3D, which is very, very complex. Of course, you have a lot of symmetry points, but also the 3D has this powerful characteristic, which is that we can provide with this kind of structure more surface area to have photoelectric analysis. But the idea is using this kind of structuring of the transition metal oxide in order also to use the infrared light, not only to increment the surface to volume area. The other part of the project, because of course, as I mentioned, we can modify the mobility just working with photons, but also with phonons. So the other part is using thermoplasmonic to enhance the mobility just to heat up the transition metal oxide and also increment the hopping mechanism within the transition metal oxide. So of course, the first idea was use this kind of isosbestic dimer metasurfaces, which should disentangle the heating part from the concentration of the light, which is also a phenomena that can happen in this kind of system. And also we can have, for example, charge transfer. So if we if we have to be very, very precise in terms of, I know that is the thermal is a thermal effect that enhances the mobility. We also should disentangle those effects. On the other side, also is reported by the literature that lattice resonances, so the distribution of some nanoparticles and some nano units of plasmonic structures can eat more efficiently in terms of quantity of scattered and also absorber for unit area. So those systems should be very, 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 very nice for this kind of application. And that's all. It was just to thanks to all the collaborators, the group of FSL, of course, some collaborator from Unimore and also Electra, and of course also IIT. And that's it. Thank you for the attention.
Thanks a lot, Stefano, for nice talk. Other questions?
Thanks, Stefano. I saw the large Polarons have like binding energies of like 10 millieV.
Yeah,
so I guess you're only going to see this in like cryogenic states, so you have to cool it down. So for real world effects, it's not going to be a major point. I imagine the large Polarons.
Yeah, exactly. The probably in that case is
the small Polarons, on the other hand, got much bigger binding energies. You're saying that it limits the recombination. So when you form the small Polaron, you create a reservoir of states for photocatalysis, so that like it lengthens the lifetime of the carrier involved. Or
for the project, you mean?
But for the project and in general.
The main idea is that when you just create the small Polaron, the recombination is, and we also saw that is limited, the recombination, because those trap state stay alive for a long time.
Okay.
And the idea is just if you use the infrared light in that case, should increase the re-excitation and then the mobility overall of the system. But maybe I didn't.
No. It's more just the point. So I had one other question about the thermite reaction.
Yeah.
I didn't quite catch the fact you're talking about red shifts and blue shifts.
Yeah.
One was the red shifts. So you're essentially heating the aluminium underneath, because that's the aluminium.
The aluminium should be
okay, you shift the edge of the aluminium. That's fairly clear to me. On the other hand, you were saying that there are two effects on the iron edge. One is a blue shift and the other is a red shift. What were the two shifts? I didn't quite.
Okay, sorry.
Maybe I didn't understand.
So the blue shift was like the one that we observed. The higher blue shift was the hematite one. Okay, the blue one is the hematite. Okay, so this delta E is just the variation from the start, the starting of the excitation to the final part. Okay, this shift is higher for hematite and lower for the thermite. So probably what happened is that you have like deformation also in the thermite of Polaron, but this blue shift is contrasted by the red shift due to the formation of FeO. So you have when you reduce the hematite, you have a red shift.
Okay. So
And
in
when
the
you
thermite
go-
alone, obviously you can't. In the hematite alone, you don't get reduction.
Yeah.
Whereas in the thermite, you can get.
Yeah, exactly.
Okay.
Exactly. That case, the formation of Polaron probably reduce also the possibility to have the reduction of hematite, and they are competitive.
They're going opposite
Yeah,
directions.
exactly.
Okay.
That was our interpretation of the. I mean, it's quite difficult to, but I mean, it was. Compatible with the calculation and also with what we saw from the little.
Here, obviously, you can't say anything about the formation time of the boron because it forms
Exactly.
immediately, essentially.
Exactly.
Okay.
Exactly.
Thank you.
Other questions? Yes.
If I'm not mistaken, I remember from textbook that there is a criterion for small polarons, the value of lambda, dimensionless electron photonic interaction. But
Yeah.
just for my understanding, what is the value of this parameter here?
Okay.
Just
Sorry.
to understand, this is a real small polarons or just, I don't know, and just or lambda less than one or larger than one?
I mean, sorry. Can you repeat the question? Sorry.
So what is the typical value of lambda?
Of lambda.
Dimensionless electron photonic interaction coefficient in order to that you repeat a lot of times small polarons.
Yeah.
But there is a criterion. What does it mean, small polarons, from the quantitative point of view?
You mean I mean
The first plate you show the effective mass of polaron.
Yeah.
1 plus lambda, if I'm not correct.
wait.
Landau-Becker model.
Yeah. Okay.
No, just probably before.
Sorry. Just before.
Okay, just because there is a mass, right? Effective mass.
Exactly.
And you can just define this effective mass as the product of the electron mass.
Yeah.
1 plus lambda. And what is the value of this lambda?
I mean.
But in general, I mean, from my experience and the experience we had with Stefano, so we characterize the small polarons with structural spectroscopies. So if you see that the environment, the first environment is perturbed without propagating on larger scale.
Across the lattice.
Yeah.
So just very localized.
Yeah, localized.
So you did not take into account other sites, neighboring sites.
No, we didn't.
No, we have not performed any type of theoretical calculations.
No, I mean,
Obviously, we are open.
No, because I'm asking like a theoretician because it's obvious that you use the term small polarons. So I just it's normal to ask.
In the case, for instance, of cerium, the 4Fs are orbital, very localized, and then when you excite a 4F, there is a small perturbation of the environment, of the edges, of the nearest neighbors.
Sites.
Yeah, and this was, I mean, I can show you some result of our group also with Stefano. And so no theoretical calculation.
No.
Okay.
We just, I mean, for those results, we just, I mean, starting from calculation from the literature, we just observe for the case of the serum, we just observe the same energy shift induced by the by the formation of the Polaron.
Oh, because then you compare with the, I don't know, DFT calculations, for instance. DFT
Yeah,
model is just, you know,
Yeah.
a linear model.
yeah.
It depends on the value of lambda. So if you, in this case, you need just to introduce nonlinearity.
Okay.
You model just to, in order to, I don't know, to fit your experimental
No, in
results.
our case, the approach was a little softer. So we saw only the deformation.
No, of course,
the
because of
lattice,
small Polarons, yes.
small Polarons,
Yeah.
yes. And this approach was confirmed also by time resolved EXAFs when we saw the effective
So the problem is that here is, I mean, those are classic Polaron. Okay, so
What do you mean plastic Polaron?
yeah, classic Polaron in terms of usually you can study Polaron like when you, introduce a defect in your structure and you have the localization of the curve. In our case, we study Photoinduced Polaron, which are related to the fact that you you excited the sample, you excited the material, you have this auto localization from the conductive. I know that is classical or not correct. I know.
Theoretical calculations on the formation of the Polaron, do they exist?
No, there is, for instance, if I'm not wrong, a nonlinear Holstein model to take into account if you consider the case of lambda larger than 1.
Yeah, but that's
one,
more of it's a static.
Of course, it's
simulation.
static, yes, but if you just, of course, in this case, I'm scary to pronounce this Keldish.
Questions? Other questions from the net? Okay, so let's thank again Stefano. Bene, vai.